Good morning to one and all. The title of the chapter is Differential Calculus. First of all, I am going to introduce myself. I am Dr. M. Gayatri, working as Associate Professor of Mathematics in Government First Grade College, Vartur, Bangalore. The definition of a limit of a function is as follows. Here we are taking a function f of x. That means a polynomial or any trigonometric or exponential function in terms of x. That means here f of x may be equal to any exponential function or trigonometric function or any polynomial, but it is in terms of x only. This function tends to a limit L. F of x tends to a limit L if as x tends to a. That means whenever x approaches to a, f of x approaches to L. If for every epsilon greater than 0, here we are considering one positive quantity, that is epsilon, but this epsilon is very small positive quantity, then there exists a corresponding positive real number delta. That means for each epsilon greater than 0, there exists delta greater than 0, such that modulus of f of x minus L less than epsilon. Whenever modulus 0 less than mod x minus a less than delta. So, once again, f of x tends to a limit L as x tends to a if for every epsilon greater than 0, this epsilon is very small positive quantity. Corresponding to this epsilon, there exists one more positive real number, that is delta. That means delta also greater than 0. These epsilon and delta are such that modulus of f of x minus L less than epsilon. Here epsilon is a positive quantity. Even though this is positive, this is very small. That means the difference between f of x and L is negligible. Whenever the difference between x and a is negligible. This is denoted symbolically by limit x tends to a f of x equal to L. So, whenever f of x tends to a limit L as x tends to a, then we can easily say that modulus of f of x minus L less than epsilon whenever 0 less than mod x minus a less than delta. If we have this condition, we can write this condition. If we have this condition, we can write this condition. That means this is implies and double implies. Now we are moved to left hand limit. This definition is same, but the condition is a minus delta less than x less than a. This is only the difference. Observe, a function f of x is tend to a limit L as x tends to a if for every epsilon greater than 0, however small. This epsilon is positive. This is very small positive quantity. There corresponds a positive real number delta. This is also positive. Delta is greater than 0 such that modulus of f of x minus L less than epsilon whenever a minus delta less than x less than a. Here previously we have mod x minus a is less than delta. This means this can be written as minus delta less than x minus a less than delta. Here we have minus a. This minus a goes to this side. It becomes positive. So, a minus delta less than x less than a plus delta. That means x belongs to open interval a minus delta comma a plus delta. Here open interval means a minus delta to a plus delta. Open interval means the set of points inside this interval. In this open interval, the end points does not existing. That means x is any point inside this open interval. This is for previous definition. Here, if we take a is here, x lies between a minus delta and a. So, x lies between a minus delta and a. In this region, x is any one point. Observe, x belongs to a minus delta comma a. In that situation, f of x belongs to L minus epsilon and L plus epsilon. Here also same thing. Modulus of f of x minus L less than epsilon implies minus epsilon less than f of x minus L less than epsilon implies L minus L comes to this side as positive L minus epsilon less than f of x is less than L plus epsilon. Whenever this is true, this is automatically true. That means f of x belongs to open interval L minus epsilon comma L plus epsilon. This is denoted by limit x tends to a minus 0, f of x equal to L, or limit x tends to a minus f of x equal to L, and is called left hand limit. Here this place is left side of a. That's why we are called this as left hand limit. Once again, a function f of x is said to tend to a limit L as x tends to a if for every epsilon greater than 0. That means epsilon is a positive quantity. Even though this is positive, it is very small positive quantity. For each epsilon greater than 0, there exists delta greater than 0 such that the difference between these two is negligible. Whenever x belongs to this region, that means x belongs to this region means f of x belongs to this region. This is also open interval, that is, this is L minus epsilon, L plus epsilon. In this open interval, f of x exists. This is denoted by limit x tends to a minus 0 f of x equal to L, or limit x tends to a minus f of x equal to L, and is called the left hand limit. Now we move to right hand limit. The definition is same as left hand limit, but x belongs to this region. This is a minus delta, a plus delta. Now x belongs to this region. That means open interval a comma a plus delta. So listen, a function f of x is said to tend to L as x tends to a if for every epsilon greater than 0. Here also epsilon is positive quantity and it is very small positive quantity. Corresponds to this epsilon, there exists delta greater than 0 such that this epsilon and delta are existing by satisfying these two conditions. Modulus of f of x minus L less than epsilon whenever a less than x less than a plus delta. That is, x belongs to this region. At that time, f of x belongs to f of x belongs to open interval L minus epsilon comma L plus epsilon. This is denoted by limit x tends to a plus 0 f of x equal to L or limit x tends to a plus f of x equal to L, and is called the right hand limit because this is right side of a. Now limit x tends to a f of x equal to L. That means for this f of x both left hand limit and right hand limit exists and they are equal to L. While doing problems you can easily understand this statement. So that is limit x tends to a f of x equal to L if and only if the LHL value is L and RHL value is also L. Next we are going to prove uniqueness of a limit of a function. The limit of a function at a point, if it exists, is unique. That means if limit x tends to a f of x exists, it is unique. That means here the L is unique. Okay, now we want to prove that L is unique. Suppose the limit of f of x, exists. So limit of f of x exists and is not unique. What we want to prove? We want to prove it is unique, but we are taking it is not unique. At the end we get contradiction. Y means we are taking limit of f of x is not unique. Then this statement is wrong. Then what is the correct statement? The limit of a function at a point is unique. So limit x tends to a f of x equal to L1 and limit x tends to a f of x equal to L2. L1 and L2 are not equal. Why we are taking L1 and L2 means limit of a function is not unique. Unique means same thing, we want to get same thing. But here we are taking not unique. That means here we are taking L1, here we are taking L2. Since L1 not equal to L2, then their difference is, modulus of their difference is compulsory greater than 0. So observe 2 is not equal to 3. So modulus of 2 minus 3, that is modulus of minus 1, that is 1 greater than 0. If we take this combination 3 not equal to 2, in this case also 3 minus 2 is 1, mod 1 is 1, so this is greater than 0. That means whenever L1 not equal to L2, then modulus of L1 minus L2 is greater than 0. So again epsilon is greater than 0. So 2 into epsilon is greater than 0. That's why we are going to take 2 epsilon equal to modulus of L1 minus L2. This is greater than 0. Now limit x tends to a f of x equal to L1. Now we are going to apply limit definition. That is, for every epsilon greater than 0, there exists a real number delta 1 greater than 0 such that modulus of f of x minus L1 less than epsilon whenever 0 less than mod x minus a less than delta 1. So you can observe here we are taking epsilon greater than 0. For this epsilon greater than 0, there exists delta 1 greater than 0 such that here we have f of x, here we have L1. Take this one and this one. The difference of these two is negligible. That is modulus of f of x minus L1 is less than epsilon. This will happen when means whenever 0 less than mod x minus a less than delta 1. Take this as equation 1. Again we have limit x tends to a f of x equal to L2. For this one also we are going to use same definition, that is limit of a function. So limit extends to a f of x minus L2. For every epsilon greater than 0, there exists a real number delta greater than 0 such that modulus of f of x minus L2 less than epsilon whenever 0 less than mod x minus a less than delta 2. Observe, here we have L1, that's why we are going to write L1 here. Here we have L2, that's why we write L2 here. Here also extends to a, here also extends to a, that's why x minus a. For this epsilon, there exists delta 1. For this epsilon, there exists delta 2. Next, we are taking delta as minimum of delta 1 comma delta 2. That means delta is the smaller of these two quantities. That means delta 1 and delta 2. So, delta is, if delta 1 is 2, delta 2 is 3, then minimum is 2. Delta is 2 only. Then equation 1 and equation 2 can be rewritten by replacing delta 1 and delta 2 by delta only. So observe, equation 1, f of x minus L1 less than epsilon as it is, modulus of f of x minus L2 less than also as it is, but here we replacing delta 1 and delta 2 by delta. Next, consider modulus of L1 minus L2. Here we are rewriting this modulus of L1 minus L2 as modulus of f of x minus L2 plus L1 minus f of x. Observe, this is positive quantity, this is negative quantity. These two quantities get cancelled, then we are going to get L1 minus L2. That means the value does not changes, only the form of this modulus changes. Now we are writing separate modulus for these two terms and separate modulus for these two terms by using the concept modulus of a plus b less than or equal to mod a plus mod b. So here we are going to get these steps. This is, take this as a, this as b. At that time mod a means this one plus mod b. Next, this term is as it is. We are going to change the position of these two terms in this modulus. Y means modulus of 5 minus 4 is mod 1, that is 1 only. Modulus of 4 minus 5 is modulus of minus 1, that is also 1 only. That means inside the modulus we can change the terms. That means modulus of L1 minus f of x is equal to modulus of f of x minus L1. But we have equation 3. From this we can easily write this modulus of f of x minus L2 as less than epsilon. Modulus of f of x minus L1 is less than epsilon. Here we have, so replace less than. Here observe, this term is, this modulus is less than or equal to this one. This one is equal to this one. This one is less than epsilon plus epsilon. Epsilon plus epsilon is 2 epsilon. Observe, from the starting to ending, whenever we get one strictly less than, at the end also we are going to write strictly less than. So already at the starting only we have taken 2 epsilon means modulus of L1 minus L2. Observe this one. Here the same quantity, here also same quantity. Observe, 2 is less than 2. Is it true? It is false. That means this is false. Why we are going to get this means? Because of our assumption. What is our assumption? The limit of a function is not unique. That means we are going to get wrong concept. That means limit extends to a f of x is not unique is wrong. Then what is the correct one? Limit extends to a f of x is unique. That means L1 and L2 are not different. Those two quantities are equal. This proves that limit of a function at a point when it exits is unique. That means limit of any function is unique, but the condition is limit is exists.